Hello Chem 1B, this is chapter 22, lecture video 1, and this chapter is primarily going to be about transition elements, the transition metals, and their chemistry. This lecture video 1, will be review. We'll be going into a little bit of naming compounds of transition metals and electron configurations and stuff like that. So pretty useful, especially if it's been a while since you took Chem 1A. So first things first, hopefully you do know where the transition elements are. The transition elements are this whole blocks on the periodic table. These are our transition elements. This is what we're going to be focusing on for this chapter. So a transition metal is really just a D block element that has at least one ion with a partially filled d orbital. So that's that whole block that we just saw. If we look at electron configurations, there are a number of different electron configurations that don't follow the normal filling rules, some of which you probably learned about in Chem 1A. I, for instance, make sure my students know these exceptions. These are the only exceptions I need you to know, the ones I've highlighted in red here. There are more, technically 5 more, but you should know at least chromium, molybdenum, copper, silver, and gold's exceptions to the normal filling rules for electron configurations. Again, this should have been covered in Chem 1A, but if you're rusty on your electron configurations, then go back and review. If you have any questions, just let me know. But again, there are a bunch of exceptions to the normal filling rules. You can see them all kind of like shaded a little bit differently. Here are the ones that aren't being required that you know them. Right, so I don't need you to know the ones I'm putting in blue here. I do need you to know the ones in red. If I give you a problem with those other ones, then just do normal filling rules. That's totally fine. Why are they called transition elements? This is something you might not have learned in Chem 1A. The reason why they are transition elements is because as we go through the periods in the transition block, or the D block, they transition across. They lie between the highly reactive metals, the S block, and the less reactive metals, the P block. Like aluminum is not a very reactive metal. There is a steady transition of properties from one to the next as we go across a period. For melting points, density, oxidation states, reactivity, and so we can kind of see that as we go across the table. What do all chemical reactions have in common? This is an important thing to kind of understand when talking about a lot of the chemistry we're going to talk about here. They all have to deal with a transfer of electrons. Either something sharing electrons in like covalent bonds and electrons are being shared between the two elements, or there's a full transfer of electrons. In our case, it's mostly going to be transfer. Which of these two is more reactive? Is it neon, a noble gas, or sodium, an alkali metal? Hopefully we all know it's sodium. Sodium is more reactive. Noble gases generally aren't reactive. Why? Let's look at their electron configurations. Neon and sodium have almost exactly the same electron configuration. The difference is this 3s that we have for neon or sodium that we don't have for neon. Why is that extra one so important? Well, this one valence electron by itself really doesn't want to be there. If we remember from Chem 1A, sodium really likes to give up its one valence electron to have a +1 charge. And the reason it does it so that it can be more stable, like neon. That unpaired electron is really the big deal. If you remember valence bond theory in Chem 1A, you probably learned that it's the unpaired electrons that are being used to form bonds or really do chemistry. In general, a compound with more, or an element with more unpaired electrons is going to be much, much more reactive than a compound with all the electrons paired up. The ideal gases have all their electrons completely paired up. However, the transition metals, because of those d blocks electrons, they tend to have quite a bit of unpaired electrons. In many cases, up to 5 or 6. The majority of transition metals can form ions with more than one oxidation state. In addition, for instance, chromium could either have an oxidation state of 3+ or 6+. Some of them can have even more than that, like manganese is kind of notorious for having a bunch of different oxidation states. Electrons are always removed from the valence s orbital before we even touch removing the d orbital electrons. And again, this is something you should have learned about electron configurations in Chem 1A. And I'm sorry I'm going fast, it's because this is pretty much all review. Again, the d5 and d10 electron configurations in the d orbital are incredibly stable. And because of that, we have that electron from the 4s or the 5s and so on jumping ship into the 3d or whatever energy level you're at for chromium's column and silver's and copper's column. Sorry. This is why we don't have them fitting the normal pattern for filling electrons in terms of electron configuration. Just to give you kind of like an idea, here's a bunch of the transition elements in the first row of the transition block. In other words, period 4. If we look at how many unpaired electrons is in scandium, it's just 1. It has only one common oxidation state, 3+. This is when we lose these two 4s electrons and the 3d electron. Titanium has these 2 unpaired electrons. Now, it has only one oxidation state, 2 usually, and that's due to the loss of these 2 s electrons first. Those ones go away first, and then these 2 as well, giving a +4 oxidation state. If we look at vanadium, it has 3 unpaired electrons, all 3 of these. It has 2 different possible oxidation states. Either you lose all or just almost all. All right, so this would be losing 4, here's losing 5. And this is how we get those oxidation states. The oxidation state 5 is more stable than the 4+, because we get rid of all these guys. And we have the same electron configuration as the previous noble gas. But that's not something I would really need you to know, per se. Chromium has 6 total unpaired electrons. 1, 2, 3, 4, 5, 6. Again, it's one of those exceptions to the normal filling rules. It has both a 3+ and 6+ oxidation state. The 3+ oxidation state is when you lose 3 electrons, so 1, 2, 3. The 6+ is when you lose all of them in the valence shell and the 3D. Manganese has 5 unpaired electrons. We're kind of going back down now. So it goes up for a while, then it goes back down as far as unpaired electrons, and that's kind of how our reactivity goes. Scandium's pretty dang reactive, but it's not as reactive as chromium. And then as we go past chromium, we start seeing reactivity start coming back down again. Manganese actually has 3 stable oxidation states. It can be 2+, where we just lose these 2 and that's it. It can be 4+, where we lose these 2 and 2 more. Or it can be 7+, where we lose all of these guys. Iron has 4 unpaired electrons, 2 possible oxidation states. Either we lose these 2 and that's it, or we lose just that, the 3. This is a very stable state. Iron 3+ is more stable than 2+, and the reason why is because you have these 5 unpaired electrons in the D block, which create, again, a very stable configuration. So this guy's more stable. Cobalt has 3 unpaired electrons, these guys. It has 2 oxidation states as well. Again, one where we lose just these 2, and one where we lose those 2 and one of these. Nickel has 2 unpaired electrons, and its most common oxidation state is just 2+, where we just lose these 2 electrons, and that's it. Copper can be either +1 or 2+. 2+ is actually more stable. It occurs when we lose this guy, 2+ is more stable, and one of those. It's kind of a fluke to our normal rules. Zn has no unpaired electrons, and it has at least a 2+ oxidation state. We lose these 4 s electrons, and that's it. So this kind of gives you an idea, hopefully, of what's going on here with the transition elements, their possible oxidation states. I do not need you to memorize these. Please don't. Just kind of gives you an idea of some of the common oxidation states for these elements. So let's talk about an electron configuration. Oh, well, the answer is 4. If we want to figure out how many unpaired electrons are in Fe2+, we can do that using electron configuration. So we write out the electron configuration of Fe. All right, so if we look at Fe, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 6, sorry, 3d6. And so if we have a 2+ oxidation state, hold up, my bad. This should be, yeah, it was 6. So if we look at this, right, Fe2+ loses these 2. If we look at this 3d orbital, 1, 2, I'll change color as we go down. It doesn't appear as well. 1, 2, 3, 4, 5 orbitals, and 1, 2, 3, 4, 5, 6 electrons in that orbital. Well, here are our 4 unpaired electrons. All right. Okay, so a little bit more review. Remember, when we're naming compounds that contain transition elements, we have to include the oxidation state of the transition metal in the name for the compound, right? So Roman numerals are what we use to indicate what the charge is on that transition metal. For instance, in Fe2SO43, we know that iron has a 3+ charge in this compound, so we have to write Roman numeral 3. And we know that because this guy has a -2 charge. There are 3 of them. That gives me -6 here. And that means these 2 Fe's have to add up to 6+. Well, there are 2 of them, so each one must be 3+ for this ionic compound to be neutral. CuCl, we know Cl is -1. Copper must be +1 to balance the charges, so this is copper 1 chloride. And finally, there's chromium oxalate, specifically with chromium having, again, a 3+ charge. So this should be all review. You definitely learned how to do this in Chem 1A. So as always, if you have any questions, please feel free to email me or come to a discussion session.